So you've seen this trick, right? Magician has a stack of fine china sitting on a table. There's a silk tablecloth underneath. The magician grabs the tablecloth, and with a big yank, the tablecloth is gone, and the glasses remain untouched. Let's figure out what's happening. I chose to use a laundry bottle instead of fine crystal. The laundry bottle had a mass of about 1 kilogram. Now I estimated the coefficients of friction to be static friction around zero point 0.4 and kinetic friction to be about 0.25. Those do not have units. And we want to know two things. One, what is the fastest that I could accelerate the bottle just by pulling on the cloth, but without the bottle beginning to slide off the back? And the second, when I really yank on the cloth so that the bottle does slide off the back, what is the acceleration in that case? As always, when we do force problems, we're going to have a strategy that we follow to help us figure out what to do. The first thing we're going to do is draw a picture of the scenario with the coordinate system. Then we're going to draw a free body diagram of all the forces on the object that we're interested in. And we're also going to have a type, agent, and object listed for each of those forces. We're going to write down every value that we know, and then we're going to write down equations either from the free body diagram directly or from Newton's second law. Usually we're going to have an equation in the x direction and an equation in the y direction. Then we might have additional equations for individual forces. For example, we know that weight is equal to mg. Then we're going to solve those equations algebraically for the requested unknown value. In this case, both of those unknown values are accelerations. Then we're going to plug in known values with their units into those equations, and then finally solve for the final value with units.
How can we understand that problem? Well, there are basically 4 phases to that. So in the first, we have the bottle just sitting there. So we have a picture. Let's put a little coordinate system on here so we know what's what. We'll use our standard coordinate system. And in that case, there's no motion. Right. So if we were to draw a simple little free body diagram, draw better ones later, we'd have normal force pointing up and weight pointing down. Let's go ahead and add a little tau chart. So we have the normal force. The agent of the normal force is basically it's the cloth, and the object is the bottle. And then we have the weight. The agent of the weight is the earth, which is pulling down on the bottle. In the next phase of motion, we begin pulling on the cloth. So we have an acceleration pointing this way as we begin to move the bottle. But the bottle is sliding along with the cloth, right? So both the cloth and the bottle move at the same rate. So since there's no sliding between the bottle and the cloth, what kind of friction do we have? It's actually static friction, right? So we'll draw, again, a better free body diagram in a little bit. We still have the same weight and normal as before. We're going to add a little bit of static friction. So in our free body, in our tau chart, we're going to have static friction. The agent is the cloth, and the object is the bottle. In the next stage of motion, we have cruising. I'm just dragging the cloth and the bottle at a constant speed. Well, what does Newton's first law say if we have an object moving at a constant speed, there must be no net force. Well, if that's the case, all we have is the normal force and the weight, and there is no force in the left or right direction, right? Because if there's still a force pointing to the right, Newton's first law would tell us that there has to be an acceleration on the bottle to the right. So those three situations explain the motion of the bottle while it was stuck on top of the cloth. Well, what happens when you yank the cloth? Well, in that case, the cloth is not stuck to the bottle anymore, right? So we have the bottle and the cloth. The cloth is moving very fast. The bottle is only going a little bit, but both are being accelerated. I am directly accelerating the cloth, and the cloth is somewhat accelerating the bottle. Maybe a better magician could make the acceleration of the bottle even less, so that you'd barely see it moving at all. Still couldn't make it exactly zero. Now, in the normal explanation of this demonstration, we say that it's the inertia of the bottle that prevents it from moving. And this is true, but it's not the complete story. So, if we look at the bottle and we see it did move, how could we explain the motion of the bottle? Well, the cloth is still rubbing against the bottom of the bottle. So if we draw a real quick free body diagram, still have our normal and our weight of the bottle. But since the cloth is dragging against the bottom of the bottle, there is a friction force. But now there's a sliding motion between the cloth and the bottle. So we do have kinetic friction this time. So with our tau chart, type of force is kinetic friction, the agent is the cloth, and the object is the bottle. So let's actually pose a question. So our problem asks us, first thing we want to find is what is the fastest we can accelerate the bottle without it sliding off the back of the cloth. Now, the first thing we always want to do with the problem is to draw a picture. Now, we've already drawn a picture. We did it on this page. And we have a coordinate system. So we've drawn a picture with a coordinate system. So now we want to draw a free body diagram. We've done a little one. Let's draw one with tick marks so we know for sure that we have a semi-quantitative one. Now, I like to always start with weight. So we'll draw a weight, kind of an arbitrary number of tick marks. So weight vector, which is the same as gravity, right? We've already done this as well, but we'll just fill this in again, just to have it complete. Then we have the normal force pointing up. And you might want to double check with yourself, why is the normal force equal to the weight in this case? And the answer, of course, is that we have no vertical motion or acceleration, and so all of the vertical forces have to cancel out with one another. There are only two vertical forces, weight pointing down and normal pointing up, and so the upward force has to cancel the downward force. Now, we also want to write down our known values. So we are given that the mass of the bottle is equal to 1 kilogram. The coefficient of static friction is equal to 0.400. It has no units. Coefficient of kinetic friction, 0.250. Okay, and what we want to find is the maximum acceleration possible in the x direction. Now, whenever you're solving static friction problems, there's usually a weasel word like maximum, minimum, fastest, slowest, something along those lines. And that's usually a clue that we want to use the fact that at that point, static friction will be equal to the maximum static friction. And the reason for this is there is no equation on your equation sheet for static friction. There is an equation for static friction maximum. And the idea here is, as a reminder, static friction is kind of like the normal force. It gives whatever value it needs to in order to balance out the set of forces in its direction, in this case in the x direction, in order to give whatever acceleration is necessary in that direction. But it has a breaking point. And that breaking point is something we can calculate. Specifically, its breaking point is equal to mu s times the normal force. Okay? So, let's see what we calculate. First, from our free body diagram, we can see that the normal force is equal to the weight. And we know from our equation sheet that the weight is equal to mg. Now, we're not going to plug in numbers yet. We're going to save that for the end. We also know that in this case, we're going to use static friction is equal to the maximum static friction, which is equal to mu s times n. And the reason that this is equal to the maximum is because we're looking for the maximum acceleration. Of course, the larger the static friction, the larger the acceleration is going to be. Okay, and the reason we're going to use this is because all the forces in the x direction is equals to max, right? So this, we're writing down Newton's second law. What are the forces in the x direction? Everything pointing right gets a plus sign. Everything pointing left gets a minus sign. There is nothing pointing left. The only thing pointing to the right is Fs. I know a lot of these symbols look similar now. This is mass times acceleration in the x direction. This is all one symbol. This is saying static friction maximum. So we're going to substitute mu s times n equals to max. Now we're going to substitute what we got for n. We're going to have mu s times mg is equal to max. And look what we discovered here. The mass doesn't actually matter at all. The maximum acceleration that you can get is just mu s times g. And we can calculate that value. It's 0.400 times 9.80 meters per second squared, which is equal to 3.92 meters per second squared. So that is the fastest that you could accelerate the bottle before the bottle begins to slide off the back. The next question asked us to find, once the bottle does begin sliding, what is its acceleration? Notice there is no what's the fastest acceleration, what is the highest acceleration. There's just one acceleration once the bottle is sliding. The free body diagram is going to look very similar. We still have normal force and weight, and the only difference here now is that we have kinetic friction instead of static friction. Since there's only one difference, I'm only going to make that one difference to the tau chart. Okay. Many of the equations are going to look very similar. We still have normal force is equal to the weight is equal to mg. We're still going to have Newton's second law in the x direction. There's still only one force pointing to the right. And we look for our equation sheet, we see that fx has an equation. There's no maximum, there's no minimum, it's just, fk has an equation, and it's just equal to mu k times n. So we're going to plug that in on the left. See mu k times n is equal to max. We're going to plug in what we have for the normal force. We have mu k times mg is equal to max. The m's cancel out just like before. And we have the very similar solution, mu k times g. We have the known that mu k is equal to 0.250 times g, which is 9.80 meters per second squared. And so the final value that we have is 0.250 times 9.8, and that is 2.45 meters per second squared. That is the acceleration that the bottle will have while you're yanking the cloth so hard that the bottle, that's the final acceleration the bottle will have when you're yanking the cloth so hard that the cloth will slide out from underneath. So, if this acceleration is only, a little less than this acceleration, why do magicians better than I, why do they manage to not knock over the glasses? Well, a couple things. One, they're using a different material with a smaller coefficient of friction. And two, one of the things you want to do is yank the cloth so fast that even though you have this acceleration, the amount of time that the objects are being accelerated by this amount is very small. And therefore, the overall motion of the objects, if you use one of your kinematic equations, which is Vf squared is equal to Vi squared plus 2a delta x, you use an equation like this in order to calculate the motion of the objects. You'll see that they end up moving only a small amount.